All right, we will finish off here with example 6 and 7. Find the first four non-zero terms of the Maclaurin series of x sine of x minus the arctangent of x. So in this kind of example, we're going to go ahead and use a table that shows what the Maclaurin series of sine of x and arctangent of x is. Some of these series you may have actually memorized because the patterns, at least for e to the x, sine of x, cosine of x, the patterns are pretty straightforward, I would say, even for the geometric series x to the n and how that converges to 1 over 1 minus x. But in general, it is perfectly reasonable and fine for anybody to just look up the Maclaurin series for these. You don't have to rederive them each and every time you want to use them. So what I would say here is first what we're going to do is just write down. So whether we look it up in a textbook or Google it on our phone, look at the Wikipedia page, let's just say we find what the Maclaurin series for sine of x and arctangent, we find them. So sine of x, its Maclaurin series is n equals 0 to infinity, negative 1 to the n, 2n plus 1 factorial x to the 2n plus 1, and arctangent of x is the series n equals 0 to infinity, negative 1 to the n, all over 2n plus 1, x to the 2n plus 1. So it is extremely similar to sine of x. The only difference is these coefficients aren't being divided by 2n plus 1 factorial. They are being divided just by 2n plus 1. Okay. So just be careful of that and note that it is not a typo. They are very similar. So what we can do here is we don't have to work with the actual formal, compactly written summation notation. We can just write out a couple terms here. So we want to find the first four non-zero terms. Okay, first four non-zero terms. So that means when we write out our series, we want to make sure we have a constant term, a linear term, quadratic, cubic, if they are non-zero. But what if we don't have a cubic term? Well, then we have to go up a power and include the quartic term, the fourth order term. We have to keep going until we've got the lowest four non-zero terms. So sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, ... Do we need to include more terms? Maybe, maybe not. I'm just going to write out 3. That seems like a safe bet for right now. Similarly, for arctangent, we will have, this will just be x minus x cubed over 3 plus x to the 5th over 5. Remember, there's no factorials on this one, so this is not a typo. It's just very similar. Okay, so now so now if I go ahead and remember that we are actually supposed to look at what x times the sine of x is, right? X sine of x. So if I put an x here, there's an x, so this becomes 2n plus 2, or I can just think of multiplying this entire thing by x and distributing it in. So this would be x squared, 4th, 6. So essentially all of these powers of x become even. They become even. So x sine of x, therefore, is x squared minus x to the 4th over 3 factorial plus x to the 6 over 5 factorial. Therefore, x sine of x minus the arctangent of x is x squared minus x to the 4th all over 3 factorial plus x to the 6th over 5 factorial. And then I'll put the dot dot dots at the very end. We're going to subtract the terms of arctangent. So this would be minus x plus x cubed, don't forget to distribute that negative, minus x to the 5th over 5. Then we've got our other terms. So the negative x is the lowest degree, so negative x. We've got one quadratic term, so x squared. Next term is a cubic, so x cubed over 3. Then we have our 4th order term, x to the 4th over 3 factorial. And then our next highest term is this x to the 5th term. But these are already the 4 lowest degree terms. So I'm just going to put my dot dot dots right there and sort of just truncate it. We're still saying that those terms are there, but we're really only looking at this. So these right here would be the first 4 non-zero terms of that Maclaurin series. The reason why it's important to write out enough terms is it didn't happen in this case, but it could happen where, for instance, maybe the one series starts off with like a power of x to the 4th, and then the other one starts off at, x to the 0th power, so just a constant term. You don't want to just go up. You want to make sure you get enough copies of everything. Okay. Example 7, evaluate this limit. So first thing we're going to notice here is because this limit is as x goes to 0, and we know that this function e to the x has a convergent power series, Maclaurin series specifically, a power series centered at 0, limits only care what's going on right when we approach 0. So a Taylor series is a perfect way to actually, it's a perfect tool for limits in this case, since a limit only cares what happens when we go close to a certain value, and if that value is the center of a power series, then our power series is increasingly accurate as we go towards the center. So what we can do is notice that e to the x has a Maclaurin series, x to the n over n factorial, from n equals 0 to infinity. So this is this is 1, plus x squared over 2 factorial, plus x cubed over 3 factorial, so on and so forth. So this limit here can be rewritten as the limit as x goes to 0 of, I'll grab the first few e to the x terms, and I can rearrange this, so I'll put the -1 and the minus x first. Addition is commutative, right? I can rearrange it, so I'll just do that so that my dot dot dots are at the end and not in the middle of my expression. That kind of looks weird. So -1, negative x, plus this whole expression, including the dot dot dots. So +1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus dot dot dot, all over x squared. So these -1 and 1, negative x and x, cancel out. And then all of the remaining terms here, they have a power of x squared or more than x squared. So that means all these terms that remain are in fact divisible by x squared. And since they're divisible, I can go ahead and rewrite this as the limit as x goes to 0. Oh, there's no fraction now. This is just an expression, 1 over 2 factorial plus x over 3 factorial. Since we canceled x squared and x cubed, we reduced that to just x, and then we've got our dot dot dots. Now all these higher order terms that are sort of hidden within the dot dot dots, those all have more than 1 power of x. Whether it's the next term would be x squared, next term would be x cubed, so on and so forth. So because of that, when I plug in 0, this term and all these terms that are hidden away within the dot dot dots, they all go to 0. So we're left over with 1 over 2 factorial, which is 1/2. So Taylor series, Maclaurin series are very useful when it comes to computing limits as well. It's just another application of them. And that is it for Taylor series and Maclaurin series.